Hello everyone, welcome back to Next Gen Chemophiles. In our previous video, we learned about crystal field theory or CFT. CFT explained how the approach of ligands causes the d-orbitals of a metal ion to split into different energy levels. It successfully explained properties such as color, magnetic behavior, and stability of coordination compounds. But CFT has an important limitation. It considers the interaction between the metal ion and ligands mainly as electrostatic attraction. It does not adequately explain the covalent character of metal-ligand bonding. So, we need a more advanced theory. And that is where Ligand Field Theory or LFT comes in. Ligand Field Theory is an extension of crystal field theory that combines the ideas of CFT with molecular orbital theory. It provides a more realistic description of the interaction between a central metal ion and its ligands. Simple analogy: think of CFT as a magnet attracting ion objects. It focuses mainly on the attraction between the metal and ligand. But in reality, the metal and ligand can also share electron density, just like two people sharing something between them. LFT considers both electrostatic interaction plus covalent interaction. This gives us a better picture of coordination compounds. When ligands approach a metal ion, their orbitals interact with the orbitals of the metal. Depending on their symmetry and energy, these orbitals can combine to form 1. Bonding molecular orbitals, which is lower energy and more stable. 2. Anti-bonding molecular orbitals, which is higher energy and less stable. Some metal orbitals may remain non-bonding if they do not interact effectively with ligand orbitals. So, unlike CFT, LFT considers orbital overlap and covalent bonding. The simplest interaction is sigma bonding. A ligand donates an electron pair from a filled orbital into an empty or suitable metal orbital. This is called sigma donation. The metal-ligand interaction can therefore be described using molecular orbitals. Greater orbital overlap generally means stronger metal-ligand interaction. LFT can also explain pi interactions, which are difficult to describe using simple CFT. There are two important types. 1. Pi donor ligands. The ligand donates electron density from filled pi orbitals toward the metal. Examples include ligands such as Cl-, Br- and O-. Though pi acceptor ligands, these ligands can accept electron density from the metal into their empty pi star orbitals. This process is called pi back bonding. A famous example is CO. The metal donates electron density back into the ligand's empty pi star orbital. LFT retains the important idea of d-orbital splitting from CFT. For an octahedral complex, the metal d orbitals are separated into T2g of lower energy, Eg of higher energy. But LFT goes one step further. It explains that the energy difference depends not only on electrostatic repulsion but also on metal-ligand orbital interactions. Therefore, LFT gives a more complete explanation of bonding, orbital energies, magnetism, color, stability. LFT helps us understand the electronic structure of coordination compounds more accurately. It explains 1. Covalent character of metal-ligand bonds. 2. Sigma and pi interactions. 3. Pi back bonding. 4. D-orbital splitting. 5. Magnetic properties. 6. Electronic spectra and color. 7. Stability of complexes. Although LFT is more powerful than CFT, it can still become complicated. 1. Molecular orbital calculations can be mathematically demanding. 2. Exact treatment of complex systems can require advanced computational methods. 3. Interpretation becomes difficult for very large and complicated coordination compounds. Let's quickly summarize. Crystal field theory treats metal-ligand interactions mainly as electrostatic. Ligand field theory combines the ideas of CFT and MOT to provide a more realistic picture. If you found this video helpful, don't forget to like, share and subscribe to Next Gen Chemophiles. Thank you for watching.